Okay, welcome to our section 10.2, hypothesis of tests for population proportions. So recall that a point estimate for the proportion of the population with a certain characteristic is given by p hat equals x divided by n, where x is the number of individuals with the characteristic and n is the sample size. So for example, if I want to know the proportion of individuals who eat dinner out more than twice a week, I could say x equals 15. That would be the number of individuals who eat out more than twice a week, and n equals 50 is my sample size. So my point estimate is 15 out of 50, or 0.30. So what this means is 30% of my sample eat out at least twice a week. And that's estimating my proportion of the population that eat out twice a week. Okay, we also learned that our sampling distribution of p hat is approximately normal. With mean mu of p hat equals p and standard deviation sigma p hat equals p square root of p times 1 minus p all divided by n, provided we meet these three requirements. So the first one we learned was the sample is a simple random sample, or comes from a random experiment. 2, the sampled values are independent. So they're independent of each other. And the way to guarantee that is your sample size is less than or equal to 5% of your population. And 3, n times p times 1 minus p is at least 10. So if you meet those requirements, you will have an approximately normal distribution for your sample proportions, the distribution of sample proportions. Okay, now we're talking about hypothesis testing. So one of the key things is, when is something significant? So when observed results are unlikely to occur under the assumption that the null hypothesis is true, that's when we say that the result is statistically significant. And we reject the null hypothesis. So this is what we're basically saying. You have a z-score, and in our case with proportions, this is how you would find your z-score. The observed value, p hat, minus the mean, divided by the standard deviation. Right, that gives you your z-score. And since we have an approximately normal distribution, our z-distribution would look something like this. And if we get a z-score that's a lot higher than we would expect, or a lot lower than we expect, then we could say that that result is statistically significant, in which case we would reject our null hypothesis. Now there's our z-score. We say this p-value is the area beyond the z-score for a one-tailed test. So this green area is our p-value, which is almost like saying, what's the probability that this could happen accidentally? So if this p-value is really small, then this z is many standard deviations away, either above or below the assumed population proportion. And if that happens, we say, well, that's statistically significant, and we would reject our null. Otherwise, we would fail to reject the null. Okay, this is the end of part 1. Coming up, watch part 2 for the conclusion of hypothesis testing. Thank you.